So thanks everyone. Oh, sorry. Here is our presentation of the 7B fully open source MOXIN LLM. So we work from the pre-training to the GRPO-based reinforcement learning-based enhancement, similar to the DeepSeek, but then we applied to the smaller model. So this is in a collaboration work between the multiple universities and also the future way technology. And also we discussed some of the applications of our technology. For example, like the translation system applied in the GOSIM system in this year. Okay, so here is the outline, and then we start from the motivation, and then we discuss to the model release, and also including the actual applications. So the motivation is that the LLMs are having superior popularity and a lot of applications. For example, from the ChatGPT to the recently DeepSeek and also the Qianwen models. But the problem is that there is concerns on the transparency and also how to reproduce it and also the safety in the commercialization. One of the big concerns is on the Llama system, because some of the Llama models, they have the restrictive licenses. And then this kind of restricted license is going to limit the widespread innovations and actually applications, commercial applications. And also for many of the models, it is also ambiguous that whether this model is, what will be their data set. If they are using the training data or even the testing data of the evaluation data set, did they do this? And this will make some contamination of the data. And we found that among those models, some models indeed has a significant contamination of the data. And this will harm the actual application of the system. So we want to make this fully open. We want to make it satisfactory of the Linux Foundation so-called open science, such that we are going to open all of this training script, the checkpoints, the training data, and also the large language model and the corresponding applications. So some other motivations. One is on the post-training quantization. So if we don't know how this model are going to be trained, if we don't have their training data, and then we can only do the post-training quantization, and those kind of post-training quantization is having a significant accuracy degradation. They're not going to perform well. But recently there is a post-training quantization from the Llama CPP that works on the Llama CPP. That works fine. That just works fine. And before that, the GPTQ and others doesn't work that well. But then if we have the data, and then fine-tuning, setting parameters, quantization, working for many of the embodied AI and so on and so forth will make it very easy and very smooth. And we have many of the good results based on our starting of the model. So we are going to follow the model openness framework, that is MOF from the Linux Foundation. So they rate the models based on the completeness and also openness. So we follow the principles of the highest openness, that is open science, including the open source, open data, and the open access. In total, this is called open science. And then we have developed these MOXIN 7B models. We release the training codes, the data, and the model. And then we are going to make continuous commitments and improvements for the fully open source of the large language models. So we adopt the Mistral architecture and enhance from that. So the Mistral architecture is an architecture, a very good architecture that originated in France here. So we avoid Llama because Llama and its subsequent work has a lot of restrictions. And the recent series of Llama also have contamination in data. So we adopt more blocks than the Mistral 7B. Because in our observation, we found that when a model becomes thinner and deeper, and the model's accuracy can be improved. And we improve the structure from the Mistral 7B. For example, we do not use a very regressive group query attention. And we are enhanced on the tokenizer, such that we can do a mixture of experts on the tokenizer, such that the tokenizer not only works for the Latin characters, but also for the other characters like the Chinese or the Japanese or the Korean ones. And then so we use something of the MOE structure. The parameter is slightly higher than the 7B, but it is still smaller than the Llama's 8B and so on and so forth. Okay. Oh, sorry, this is not this. So in our pre-training data, we mostly use the text data plus the code data. So we got the help from the text coder team. And then they said that the coding data is not only useful in the coding, but it is also important to improve the logic of this model. In the text data, we have 3 sets of the text data. The red pajama V2, and also the slim pajama. And this slim pajama is actually a shrinked version. The red pajama V2 has a total of 20T training data. But we have made a summary, and then we found that 4% of the training data is just 404 error. It means that if you are going to crawl on this web, and then the web page doesn't open, so there is actually no data, and this kind of data is not that useful. So this is the reason that we mostly work on the red pajama version 1 and also slim pajama, while we have our tool to extract some of the data from version 2. And also, we are using this DCRM baseline, which is actually the model extracted by Apple. And also, they have a total of 3T data. So in total, we have trained about 2T of the total data, and we found that it already converges. If we are going to further improve, use more data, because, if we are going to have, instead of the 7B model, but we are having a 30B model, maybe we need 10 times more data. But in this case, we didn't find that those kind of data are that useful. Compared with Llama V3, and then our data, we only use 2T, while Llama V3 claimed that they use 15T, but we didn't see much of the difference. And then one thing is that we have optimized based on the text data and code data, where the code data is from the text coder team. And then we use those GitHub sites, and then we're collecting their data, which has a different programming language. By the way, mostly we use a programming language like C or Python, and currently we are using the Rust as well, as it's becoming more and more important. And also we have collected some other data from the Chinese and from the other languages. And this is going to reduce because the Mistral or Llama is not that good in these languages, and we are going to balance on a different set of languages. So another thing is a so-called capability enhancement. So this so-called capability enhancement is a little bit tricky. It says that if we have the different training applications or training data sets, like MMLU, like we know Grant, and then is it okay that we are going to fine-tune on their training data set? The early work claim that they have done so, but recent work, they hide from it. So they didn't mention that whether they improved on this data or they didn't improve. Of course, we can do a conventional SFT, but besides this, we also report 2 models, one with this capability enhancement and one didn't. But we're not using the test data, because the test data, if we are going to train using the test data, this is something like a violation of this is really not good. Okay. So we train using more than 2T tokens. And this is 3 phases. So we are going to train from a shorter context length to a longer context length. So we are trained using 2K, 4K, and 8K. And then we train with the capability enhancement data. So the training framework is a colossal AI. But we tested other frameworks as well. There may be some other framework that can run faster. And then we have some of the parameters that have been set that is also going to be shown here. So we have some of the optimizations. Some of the optimizations is new at that time. But also some of the optimizations is already shown before. But there is only one optimization that is still new. That is the MOE regarding the tokenizer. So the sliding window attention is a new technique for the long context when we were begin training, and also the rolling buffer cache. But then those models are applied in some of the new methods as well. So our models can support 32K context lengths. And then we can have a fast inference and also a low memory cost. So we are training from multiple aspects. This is a training for pre-training evaluations. So and then we have multiple evaluation tasks, as we can see here. And also our evaluation framework is a LLM evaluation harness. So we evaluate this base model, which is the original model and also the enhanced model. And also we have our few shot evaluation. So we are going to evaluate both the zero shot and the few shot. As in the recent work of the large language model, they show both results. So this is the few shot evaluation. And in the few shot evaluation, we can see that here is a comparison with different models. For example, like the Mistral. This is on the latest Mistral. And also the Llama 3 and the Llama 2. And also on some other models. And we can see that our model, when we use our enhanced model, the overall accuracy is higher compared with the Llama 3 8B. So we use a smaller model, but our accuracy is higher. And also we compare with this Q1. But this model, in terms of few shot, it is very strong. In terms of few shot, this is the best one. So in terms of zero shot, so here we also compare on the zero shot. And this is our advantage. And we can see that our result has the highest on the zero shot learning. This is not only better compared with Llama 3, even when they have a larger model, but it is also better compared with Q1, which is even in their 2.5, version 2.5, ours is still higher. So this is our advantage of the zero shot. So this means that our Moxin 7B can have a very good accuracy performance. And this accuracy performance is even higher, can match with the highest, with one of the best model, which is the Q1 models. So we can see that, we can also see DeepSeek here. So, but the 7B version of DeepSeek is not that strong. DeepSeek has an advantage of these super large MOE models. In terms of small models, the performance is similar compared with the others. Yeah, but DeepSeek has a very good strategy of training MOE. This is their advantage. So for the post-training, we adopt the open source Tulu-3 dataset and the framework. And then we applied both the SFT and the DPO. We have also applied the PPO, but didn't see much of the advantage here. So in this Tulu-3 SFT mixed dataset plus the open source framework. And also we have a version 2 which uses the open source Infinity Instruct dataset, which is from the BAAI in Beijing. So our have two versions. SFT means this is supervised fine-tuning, and DPO is reinforcement learning. And then we have our multiple models, SFT, DPO, and the DPO2. This is the three post-training chat models. So we can see here is the results. And we can see that our original, from SFT, our overall evaluation is 74, but then from the DPO, our evaluation is quite good. So this means that this result is even better compared with this Mistral, Llama, or Q1 when this is zero shot. Zero shot is clearly our advantage here. So we can see comparable or even higher performance here. And then this is a few shot results. In the few shot results, again, we can see that this Q1 is the strongest. And ours will be the second. So this is the advantage here. And also we can see when we use this mathematical data set and mathematical based reinforcement learning. But this is still not GRPO, this is still PPO. And then we can see that our results is becoming better on average compared with Q1 or the Gemma 2. But we didn't compare with Llama 3 in this because the result of Llama 3 is very ambiguous here. I mean, I think that this doesn't match with the actual performance. So we didn't compare with this Llama 3. So the other thing will be an important thing, which is the chain of thought enhancement. This is one of the key advantages of DeepSeek. So of course, this original reinforcement learning is from the DeepMind. And this GRPO is even better compared with PPO or DPO because it's work for the chain of thought. Originally, chain of thought, you need to mark the data when you're collecting the data for the OpenAI. But in DeepSeek's GRPO, as long as the results can be verified that it is correct or not correct, as long as the result is verifiable, and then we can use the GRPO reinforcement learning to generate the intermediate results of chain of thought, which is a very exciting idea because many of the applications, like the medicine, like the embodied AI, there is no enough data. So this kind of data generating from simulation and this chain of thought idea and the reinforcement learning is actually shed a light on the application to this wide application. So DeepSeek's original paper claims that only the large models can benefit from the GRPO. But they said that the small models will benefit a little. They say that this is not even as good as SFT. But we enhance this model, and then we adopt two frameworks. One framework is from UC Berkeley, the DeepScale R. Another one is from China, the Ariel. And then we enhanced on these frameworks and extend to our models. And then we have generated two models, which is a reinforcement learning model based on the mathematical and coding data set. And this is the mathematical results. And we can see that our reinforcement learning based on the Ariel model is already higher compared with those kind of mathematical benchmarks. And then if we use the DeepScale R plus this data set, and then the overall results can be even higher. So this shows that our model shows that the mathematical or the chain of thought can be improved by reinforcement learning even if we are using a smaller model. And also, this kind of smaller model we have compared on the two frameworks and with our model and the codes, and we found that one seems to be higher accuracy. Okay. So we have developed all of those models, and we release all of those models. So some of the models are just released. And then we release together with the training data and the training codes. And this can be helpful for the society for an overall procedure of training models, and also how this can be used in various applications. And this is our technical report or paper. And then we can see that we have the home page with all the codes, the base model, instruct model, reasoning model, chain of thought model, and so on and so forth. Okay. And then we can see that our models can have multiple applications. One of the applications is actually the real-time translation and the agents. Because we know how to train the models, so we can do a job that in the translation that has been applied in some of these rooms here. And then we can see it. But I don't know why there is no translation. Yeah, so I don't know why. What is the problem there? Anyway, I think in the other rooms, it seems works okay. So we have our on-device deployment system. There's no voice here, but anyway. We just show a demo to show that our translation system can be quite real-time, and it doesn't connect to the web. It doesn't connect to the internet. It just uses a computer here, a local host. And later we can make it on a mobile. This is also totally reasonable. Okay. And then we have our results on the large-scale MOE model deployment. So on the recent Qianwen 3 model that has just been released, this is Qianwen 3, which original model has a size of 255B. But it only activates 22B because this is an MOE model, mixture of experts. So this kind of training of the large model is beyond the capability of a research group like us. But then we can apply, because we understand how to do the training, and then we can do the characterization aware quantization together with Llama CPP. And then we can have a good accuracy on this. This is an untrained model's accuracy, as we can see on those representative data sets. And this is our results. And our results is better compared with the Anslows. They have a quantization result as well. We can see that our model size is smaller than this one. Our model set is smaller than theirs, but our accuracy is consistently higher. So our accuracy drop is consistently smaller. This is because our quantization technique is more advanced. And actually, to be honest, Anslows has released their model. This is great, but they didn't even quantize on the accuracy. So, we reported the accuracy. But seems that the accuracy is okay. But ours is even higher. Okay. And then currently we can deploy of this Qianwen 3. There is over 235B on a single notebook with the AMD. So this is actually just a notebook with this kind of size. And then it seems that we believe that this kind of DeepSeek-like MOE structure seems to be the future. And then it means that the NVIDIA 4090's trend may not be that correct. NVIDIA's trend is that this has a very strong GPU computing, but the memory is very small. 4090 only has 24 gigabytes of memory. But recently, in the AMD or Intel, there are machines with something like 128 or 96 gigabytes of the memory. And also similar to many of the chip companies in China, for example, Huawei and others. They have a large memory. Seems that this matches with the MOE very much. Because the MOE activates a very small portion. In DeepSeek, it's only 5% of the computation is actually activated. Even if we are using the A100 or H100, it seems to be a waste of the computation power and also the carbon footprint. So then, seems that this kind of notebook is quite a good way of doing this. And then currently we are working on multiple of these frameworks. And we can see that this is our speed of this kind of computation. And then we can compute as 14 or 15 tokens per second. 14 tokens per second of the full model, 235B on just a notebook computer. This is even faster compared with previous speed running the Llama 30B or the Qianwen 30B. And we have our technology of doing this. And we are collaborating with also Huawei and Intel and some of the Chinese companies, other Chinese companies on this. And here is our results on the full-size DeepSeek V3. So the original DeepSeek V3 has a total of 671 billion parameters. And then we have our unique technique to make it 85 gigabytes. We are using a combination of quantization and expert merging. If some of the experts are not that important, we can merge with those important experts. And we can see that our model, we can make it 85B, and then we can potentially run on one of a single device from Huawei or a single device from AMD. Because this size is matches. But this size, if we are using the NVIDIA 4090, we need 4 devices. So this is advantage. And we can see that our model is consistently higher in accuracy compared with a DeepSeek distilled Llama 70B. Its accuracy is always higher, and we can run 2 times faster. So then it means that the size here is 70B, and we are slightly larger, but then we are faster because ours is MOE, and we only activate a portion. So overall, ours is clearly have advantage. If we have this kind of results, then we should always choose a reduced size DeepSeek V3. Okay. And here is our final result on the embodied AI. The previous work, we start from the OpenVLA, which is an open source framework. And this open source VLA has a weakness, is that they start from the Llama V2. Even if we are going to replace it by a new model, the accuracy can be higher already. But then we are going beyond that. Not only replacing to our model, but we are also changing the structure to a hidden state. And also we are going to add the tokenizer as well. So the previous method is going to generate 7 tokens on 1 action. And then we are going to generate 8 actions with a single ACT token. And this can speed up the training and also inference. And we integrate our model for these applications. And during training, we have our optimizations on the loss and also our adversarial training. So the key advantage is that we can achieve a higher accuracy with less training efforts. For chunk 8, which means that we are going to generate 8 actions in together. And then we only need 1/8 of the training effort on the goal and object task. 27.5% on the spatial task, or larger training effort compared with the training of the OpenVLA. And we got higher accuracy together. So we can see this is a comparison on the accuracy. Ours, chunk 8, we are much faster compared with the OpenVLA or the OpenVLA OFT. But meanwhile, our accuracy is even higher. We are at least 8 times faster because we generate 8 actions. But meanwhile, we have an average of over 20% accuracy improvement compared with the OpenVLA, which is from Stanford. And then we can see these results. We actually applied on an NVIDIA Orin board. And we can see that previously, if we use the OpenVLA, it can only run in 1 Hertz. But now with even a higher accuracy, we can improve the speed to 23 Hertz. So it means that for any of the device, like an NVIDIA Jetson device, or even on a mobile phone or any of the embedded device, we can let it to control the VLA or VLM for the embodied AI. So later we do not actually need a server. We can use the integrated computing capability, and then everything is real time. And meanwhile, we improve the accuracy. So this is clearly have our advantage. So thank you very much.